We are going over when to use, how to use, and 4 examples of using the law of sines, aka the sine rule. The first question you want to ask yourself, is the triangle right angled? Meaning, does it look like these on the left or does it look like these on the right? These on the left, in fact, are our right angled triangles, as you can see by the little square box in each corner. These typically represent a 90-degree angle, aka right angled. These on the right, who knows what these angles are? We have absolutely no idea. They're totally random in shape and totally random in angles. So you might ask, why does it matter if the triangle is right angled or not? While right angled triangles can be used with the law of sines and the law of cosines, it's not preferable. These are more complicated equations and methods, and right angled triangles have their own equations that are typically easier to use than those of non-right angled triangles. For instance, the Pythagorean theorem and SOHCAHTOA. These are strictly only for right angled triangles, and they are much easier to use to solve both angles and sides than using the law of sines or law of cosines. On the other hand, the Pythagorean theorem and SOHCAHTOA cannot be used with these triangles without the right angle. We have to refer to the law of sines or the law of cosines. Either one can find either the sides or the angles we want. They're just a bit more complicated, as you can see by the formulas. In other words, the law of sines is best often used only with a non-right angled triangle. If you're dealing with a right angled triangle, you're better off using the Pythagorean theorem or SOHCAHTOA. These can be used here, but these cannot be used here. Therefore, most often, you will see the law of sines being used for non-right angled triangles, and that's what we're going to do today. So moving on, we're going to be discussing the sine equations and also how they fit into the triangles themselves. So here you can see our first equation. We have the non-capital letters on the top. These represent sides of the triangle, all 3 sides, and then the capitals on the bottom here represent all 3 angles of the triangle. Basically what this equation does is relates each side to its opposite angle on the opposite corner of the triangle, the sine of that angle. And it uses this ratio to find another side in its opposite angle. It's pretty neat how it does this. To actually use this equation functionally, you need one side in its opposite angle. So let's say we have little a and big A. And then let's say we also have big B. Then we can go ahead and we can find side B, little b. There's no other way to really do this except for using this equation. If C had nothing to do with the problem, it wasn't given to us, we're not solving for it, you can totally disregard any section of this equation just to find the other 2. They're all equal to each other, which means they all don't necessarily have to be used in the equation at once. The second equation has the larger capital letters on top and the smaller letters on the bottom. You might be wondering, what's the difference between these 2 equations? Well, not much. They're pretty much just used for convenience sake. If we have the little letters on top, the sides, we're solving for a side. If we have the angles on top, the capital letters, then we're solving for an angle. And all this does is simply save a step in the algebra to get to your solution. So now moving on to our triangle. You can see that like we discussed up here, we know that the top and bottom are opposite each other on the triangle, so little a and big A, its side and the angle are opposite one another, and we can see that right here. So as you can observe, these are completely opposite one another on the triangle. They're not adjacent, they're opposite. The same goes for C, and the same goes for B. So let me just plug some numbers in for these variables real quick so we can actually see how we could solve a problem here. So let's say little c is 5 meters. Let's say capital C here is around 40 degrees. And then let's say we have big A here as well. We have this angle. Let's say that's 80 degrees. Now we're trying to find little a, this side down here. Now if we look at our equation, we have little c and big C, so we can plug those in right here. We have these 2 variables already. And then now we're solving for little a, and we also have big A. So we have big A here. Now we can cross out B like we did up there. And now as you can see, we have narrowed our equation down to 1 variable, which we can solve for. One last thing to take note of with this triangle. Let's look at angle B here, big B. Notice how this is the smallest angle on this triangle, smaller than both A and C. Notice how little b over here also appears to be the smallest side of this triangle. Now, look how big A here looks like it's almost 90 degrees. This is a very big angle. Look across from it. Little a just so happens to be the biggest side of the triangle. Because of these two, big C is middle-sized, if you will. It's a middle-sized angle between A and B. And the side C is also between A and B, the lengths of the sides. Angle size is directly correlated with the opposite side's side. So for an example of this, we can see this angle right here is quite large. Let's see the opposite side it creates. Quite a large side. This angle is probably around 75 degrees. Now let's go over here. Let's create around a 20-degree angle. Look how much smaller that side is. These are about the same length on the bottom. This side is significantly smaller than this side. Bigger angles equal bigger sides. Smaller angles equal smaller sides. You might be wondering, why am I telling you this? Because it's a very easy way to check your answer. For instance, if you get that A is a smaller angle than B, then you may want to go back and redo your work. Or vice versa. If you get B is larger than A, then you might want to check your work. And the same goes for the sides. So moving on to our first question here, we can see this in action. So we have a little a. It's apparent that we need to solve for little a. This is going to be our big A, because these, first off, because they're color coded, and second off, because they're on opposite sides of the triangle from one another. And then we have 4 meters here and 55 degrees here. So these are related, and these are related. So these are going to go top and bottom within one equal side on the equation here. So what observations can we first make? Well, we can say that this is little b and this is big B, because we know this is little a, so this must be big A. And we can also see that 4 meters is going to be a greater distance than A. And you might be wondering why. Well, like we discussed previously, notice how A has a smaller angle of 45 and B has a larger angle of 55. Therefore, A is going to be less than 4 meters. So what equation are we going to use for this? Well, think about it. We're solving for a side, a non-capital letter. So we're going to want to use the equation with the non-capital on top. This saves us time and extra algebra that's unnecessary. So without further ado, let's jump right in. There are 2 ways to solve these. I'm going to just be using the simpler way and not even showing the harder way because, well, it's harder and it's just confusing. So A is our variable. Below A, the angle opposite A. We know that to be 45 here. Let me label these again. Little b, big B. So we know the angle opposite of A here is going to be the sine of 45. And that's in degrees. And that is equal to the ratio between 4 meters divided by the sine of 55. Now the goal here is to get A all by itself so we can solve for A. We want all the numbers and all the functions to be on one side of the equation. Well, because we have 2 over here and 1 over here, let's move this guy to the right side. So because this is being divided by A, we want to multiply both sides by a sine of 45 degrees. This will cancel this over here, leaving us with just A, which is perfect. It's going to be multiplying sine 45 degrees over on this side. Canceling the degrees, leaving us with meters, which is exactly what we want because we're solving for a side. This is going to give us a very nice answer of 3.45 meters. So real quick, if you want to check that answer, let's look again. Big B has a larger angle than big A. Big B's side, little b, is 4 meters. Little a's side is 3.45 meters. Therefore, it's smaller than little b, which makes total sense because it has a smaller angle. So moving on to the next problem. The first 3 triangles are all the same, and then the last one's slightly different and harder in almost every way. So, like this one to the last, we have 4 meters again with the 55-degree pair. That is awesome. And we're going to label that little b and big B again. We also have little a again. We want to solve for little a. Same side as before, so we should get the same answer. Except we don't have the angle opposite it. That's a problem. Up here we can see we have 80 degrees as well. So this is going to be big C. This is going to be big A. And this is going to be little c. So you might be wondering, well, maybe we should find side little c, but that's not going to get us any closer to the answer. So we need to go directly to angle A. If you take a geometry, you know there are 180 degrees in a triangle, and if you haven't taken geometry, then now you know. So if there are 180 degrees in this triangle, and we already know 80 and 55 are already factored out, then the remainder must be within our last angle, big A. So to find big A, we're simply going to take 180 degrees, the anglage in every single triangle. We're going to subtract 80 degrees from that, and we're also going to subtract 55 degrees because we already know 2 out of 3 angles. And the remainder of the degrees that are allowed in each triangle should give us the angle for big A, which comes out to be 45 degrees. So now our problem is exactly the same as before. Now that we have the angle opposite of little a, we can solve for little a. Now we have 3 knowns in the equation. We have little b, and big A. Before we did not have big A, leaving us with 2 unknowns, making the equation impossible to solve for. So without further ado, a over sine of 45 degrees is equal to little b, which is 4 meters, over big B, which is sine of 55 degrees. And then we want to multiply both sides by sine of 45. Whatever's in the denominator under what we need to solve for, that always needs to be multiplied by both sides. If you can just remember that, it makes it a lot simpler. So the sine of 45 right there. And then we're all ready to go. The degrees cancel, leaving us with just our unit of length, and A equals 3.45 meters. Awesome. So next, things get a little bit darker. No more colors anymore. So same triangle as before, except for no more colors. We have 4 meters and 55 degrees again across from each other. Hope that's not getting too repetitive. And now we solve for the side twice, so we know that's definitely there. Now we're looking for the angle across from it. So what equation are we going to use this time? Well, because we're finding angle, we want the angle on top. And that's really all that changes here. So we can cross out sine of c over little c because they have nothing to do with the equation, similar to the last couple. So we have sine of a, that's what we need to solve for, is the sine of a. That's going to be over the side opposite of the angle A, which is 3.45, and that's meters. And that's equal to the sine of big B, which is 55 degrees, all over little b, which is 4 meters. So just like the last couple, we want to look for the side with the variable. In this case, it's a big A, and we want to factor out that denominator. We want to get that out of there. So let's multiply by 3.45 meters. These cancel, which is awesome. 3.45 over here. Now we have sine of A is equal to the sine of 55 degrees all over 4, and that's in meters, except for not for long. 3.45 meters. The meters cancel, leaving us with degrees, which is awesome because we're solving for an angle here. So then we have sine of A is equal to 0.7065 degrees. Now this is not the answer. We have not made it to the answer yet. We still have A in terms of sine. We want A all alone. So like before, using the opposite of division, using multiplication, we want to use the opposite of the sine function, which is inverse sine. So if you inverse sine both sides, you get A equals inverse sine, which is sine to the -1, right in your calculator. 0.7065 within that degrees. And basically here you don't have to show inversing the sine, it's basically too repetitive, so we're just going to cross that out. Then you get the A, and then you can just go ahead and type this in your calculator. So when you get to this point, just disregard the sign and just do inverse sine on the opposite side of the A, or the variable. So once you plug that into your calculator, you should get 45 degrees, which is awesome because that's what we were looking for, and we know it's 45 from previous questions. Playtime is definitely over with this question. With 42 degrees up here and 22 centimeters down here, and it looks like they are opposite one another, because in fact they are. So we know those two are a match. They're a pair because they're opposite. Then we have 30 centimeters here, but we have nothing across from it. We're going to go ahead and label this one B, and we're going to label this big B. We're going to label this one little c and this one big C. Then how about we label this one across from little a, big A. because that's all we got left. So now we have everything labeled properly. So we have nothing across from little a, like before in that previous question where we used the 180-degree method. Except for now we can't quite do that because we only have one angle and we're missing two angles from that, meaning it's impossible to solve for the remainder. Then we have the 30 centimeters over here with nothing across from that either. So therefore the only way to solve this problem is using the law of sines to solve for the angle across from the 30 centimeters here, using it to find big B, and then using the 180-degree method with big C and big B to find big A, like we have done before, and then using law of sines once again with the ratio either between big C and little c or little b and big B alongside our newly found angle big A. So let's write down our equation because now we're in big boy world and we don't even have our equation. So I'm writing angles on top because first we need to solve for an angle, then we need to solve for another angle using the 180-degree method, and then we need to solve for a side. So just follow me here. So firstly, we have big C and little c and little b, but not big B. So we can cross A out here, and then we can follow our equation down here. So we have sine of big B, that's what we need to find. We know what's across from it. The side opposite is 30 centimeters. And then that is equal to sine of big C over little c, which is sine of 42 degrees, all over 22 centimeters. So basically we're going to multiply both sides by 30 centimeters. Whatever in the denominator with the variable, that cancels here. I'm plugging that in over there. And now we can go ahead and solve that right now. What's on the right side, just so it's nice and neat and looks tidy. That comes out to 0.912 degrees. Now once again we have sine of b here. This is not our answer. We need to get straight b over here, and then we need to inverse sine this side so we can get rid of the sine here. So this cancels, and we get b equals sine inverse 0.912 degrees. And then finally that comes out to a not so friendly 65.78 degrees. So now we know big B down here is 65.78. So now that we have two angles and we're just solving for one, we can now solve for angle A because we know there are 180 degrees in a triangle. Therefore angle A equals 180, then subtract off the 42 degrees, and then subtract off the 65.78 degrees. And that leaves us with 72.22 degrees left in the triangle for angle A. So now that we have found both angle B and angle A, there's only one variable left in this entire thing, little a. So we can put our 72.22 over here. So now you can see we clearly have our matching pair now. We have our 72.22 along with our little a. And we have plenty of other variables we know now to use in proportion with that little a. So now that we have our pair here, we have big A and we have little a, we can solve for little a using either our big C little c pair or our big B little b pair. We're going to be using big C little c just because it was our variable from the beginning. So we have, not that, we have a over the sine of big A because now we're solving for a side, so we want the side on top. Then we have that equal to little c over the sine of big C. That's a little c, you can see that. Okay, so plugging in, we have a over the sine of big A, which is going to be the sine of 72.22. That's going to be equal to little c, which is going to be 22 centimeters, all over the sine of big C, which is going to be 42 degrees. So now we can multiply the side of the variable by its denominator, canceling the denominator, so sine of 72.22, these cancel. Then we multiply this side by the sine 72.22. Then finally, we have a equals to all this mumbo jumbo. And if you plug that into your calculator, excuse the not so tidiness, we get a is equal to 31.32 meters. And that is our final answer. Thank you so much for watching. Please like, comment, and subscribe. It would mean everything. Tell me what you liked about this video, the formatting. If this helped you at all, I would greatly appreciate it. And most importantly, have an awesome day.